Today we are going to have a little discussion on the real-time operating system. Okay. This particular discussion is expected in this unit only, okay, but not immediately as a result of discussing with the real-time systems. Last time we have discussed this real-time systems, so today we are supposed to discuss about, or we were supposed to discuss about the issues and design approaches those are being used for real-time systems. Okay, so what your approaches those I could collect till date in so many years. Recently, 2 days back, I really got very interesting design approaches and very interesting design propositions. Those are there with real-time systems. So I purposely holded that particular discussion for maybe next topic discussion. By that way, I will be comfortably prepare most of the things which are expected to be delivered in line with the today's context. That is what I wanted to do, and that is what I'm delaying that particular session. And today I'm going to just have the discussion onto the real-time operating system, which is immediately the topic after discussion of this real-time system challenges and design approaches. Okay. Now, as we have already seen that one of the software architecture for making the system real-time is real-time operating system. As we went on to understand about the round robin with interrupt, function queue scheduling, and real-time operating system. So during discussion of real-time operating system, we have clearly mentioned that the interrupt latency or the worst case response time of this particular architecture that we call real-time operating system ideally is 0. Means immediately as on when required, this particular response can be given. Okay, so when we are saying it's a response is given, that means the response to the requirement of either an interrupt or the task switches that would be given. That doesn't mean that the task would get complete with ideal 0 time. Getting my point? So this is the basic baseline difference. When we say it's an worst case response time, it is near to 0, or ideally it should be 0. That means immediately I would be able to attend. Means reactive would be of a tall order. Immediately I would be able to attend the services which are required for that interrupt or task switching when I'm making use of this real-time operating system. Okay. Couple of discussions, we also started discussing about the MUCOS2, right? And we understood that the baseline architecture of MUCOS2 or baseline scheduler of MUCOS2 happens to be a priority-based preemptive scheduler. Again, the priority comes into picture and preemption comes into picture, right? So we have discussed what exactly that scheduling algorithms is all about. Okay, apart from this particular algorithm, maybe in the next time I'll discuss that there are different algorithms are also there for real-time system design. So what are those algorithms? Those also would be discussed very, exhaustively for under the topic of scheduling of real-time systems. Okay, but as we know, the prima facie real-time operating system and general purpose operating system. Real-time operating system is basically a category of embedded operating system. When I'm saying it's an embedded operating system, I should have a valid reason to understand that whenever I have got embedded as an appendment of word to an operating system, I have enough reasons to believe that this particular operating system should be used for a specific application or on a specific hardware with a specific kind of structural resources or memory resources. These are constraints. For a constraint environment, for the application specificness, and in order to build some kind of reactivity, in order to build the better response time of the system, I need to have an operating system, and that operating system is referred to be as an embedded operating system. And this embedded operating system, one category of this embedded operating system is real-time operating system. When I'm saying it's a real-time, in the immediate last discussion only, in the immediate last session only, we understood what exactly mean by real-time systems, isn't it? So if I need to just quickly reiterate it, the real-time systems are the computing systems or information processing systems in either of the category of any 3 C's, whose output does not really depend on the logical correctness of it, but also at a moment of time at which this output does take place. Means logical correctness and the time at which this particular output would take place is equally important. That is what logically ended in order to say or in order to classify a system to be as a real-time system, right? We have a couple of examples even we have seen in the last session that we have discussed. Now, when I'm expecting that the operating system to build up that kind of system, what we are referring as a real-time system, I refer the service time of this operating system. Service time of this operating system also should contribute into defining a system to be a real time. And in the characterization of the real time system, we have clearly said that real time systems are highly deterministic and real time systems are highly predicted. So the ability of the operating system service time, which makes the underlying embedded system to be a predicted one, is referred to be as a real-time operating system. I repeat, the real-time operating system, by virtue of having a service time, or as the service time of real-time operating system is designed, or services of real-time operating system are designed to deliver in such a way that the service time of this operating system would make the underlying system to be real-time. That means underlying system to be a highly predicted one. Now, what is the speciality of this particular service time of this real-time operating system? So characteristics of the service time of real-time operating system happens to be like this service time is constant and should be known a priori before the execution of it. That means the manual of real-time operating system should be able to clearly specify that what is the amount of time that is being taken to be as a service time. Because we have seen in the last discussions, a couple of sessions, we have seen that when we are making use of an operating system, there is the concept called no free lunch, isn't it? So each and every service that you are going to make use of operating system is going to consume some certain amount of time when the service time or when the services are expected to be explored for the underlying application and hardware. So if this particular service time happens to be constant and known a priori, or happens to be constant and known in advance before getting it execute, is it not the case that I can estimate the complete execution profiling incorporating that particular service time, which will make my system to be highly modeled, or which will make my system to be highly described with the simple algebraic equation. And any system, when that gets modeled or described by a simple algebraic equation, those systems are highly said to be deterministic, or those systems are said to be highly predicted in its nature. This is what the baseline philosophy of writing the operating system, which contributes to an embedded applications in the category of real-time operating system. Now, having discussed all this, there is an interesting statement that I always say in regards with this real-time operating system. And that statement goes like this. If someone asks like, what is the difference between general purpose operating system and real-time operating system? The prima facie answer that goes on is there is no difference between real-time operating system and general purpose operating system. Means GPOS, general purpose operating system, and RTOS, GPOS and RTOS is the same, but they are not same. Now at this particular time, I'm sure that every one of you might be wondered and puzzled even. Like, how can this fellow makes a statement where half of this, he is contradicting to half of the statement that he made in the earlier part of it. I'm saying that GPOS is same as of RTOS, but GPOS is not same as of RTOS. Isn't it a funny statement? Yes. And the reason behind this is GPOS and RTOS are referred to be same in terms of the services those they offer. I repeat, the GPOS and RTOS are referred to be the same one with the services that they offer. And in the second half, what I said that GPOS and RTOS is different. And that's what I'm saying, that RTOS offers the service differently than GPOS. And what for the difference is being there? The mechanism of offering the service by RTOS differently is in order to build a constant and a priori deterministic service time. Otherwise, general purpose operating system, as it is basically intended for achieving the throughput. I repeat, as the general purpose operating system, as it is being intended for achieving the throughput, is completely load dependent. Means whatever the load that it has to handle, whatever the number of tasks that it has to handle, whatever the number of messages that it has to handle for the process of communication and synchronization, whatever the memory size that it has to handle in order to make the common memory to be shared among the different tasks, means all the services those are being offered by general purpose operating system, they are highly dependent on the load on the system. They are highly dependent on the factors where it has got involved into this particular services. For example, the task switching service of operating system, as we know that there happens to be a context switch in between the task switch, right? So if I got the three tasks, 1, 2, 3, and each of the task has got, for example, the execution time referred to as in 4 millisecond. Then if I ask you that what is the total amount of time that you would require for an application when it has got 3 tasks and each task has got a 4 millisecond? If you're thinking of an answer like as in 12 millisecond, then let me tell you that this is wrong. Because whenever I'm having a multitasking application with 3 tasks with each of a 4 millisecond, I have to consider the task switching time in between those also. So in a 3 typical task, in a 3 task, let's say I am making a 2 task switches. So means context switch happens to be there the 2 times. Then I need to add the time which is being required for task switching service of operating system to be added up along with the task execution time of this application. And if this particular task switching time, if that happens to be a constant and is being known earlier, let's say for RTOS, this task switching time, let's say for example, this is 500 nanoseconds. When I'm saying it's a 500 nanosecond, that means this is constant and this is known also already before getting it executed. That means in the 2 context switches, I can say that 500 and 500, 1 millisecond would be the time that would be elapsed for the context switches, and the actual application, actual 3 tasks that would take up around 12 milliseconds. So 12 milliseconds plus 1 millisecond, that happens to be a 13 millisecond when 3 tasks are executed in a multitasking fashion. Isn't it not so clear? Why? Because I know the service time of operating system is constant and that is being known well in advance before an service does get executed onto it. And that is what the speciality of real-time operating system. Now, is it like the task switching service or task management service is offered only with RTOS? No, GPOS offers the task management service. RTOS also offers task management service. You name the service for GPOS or GPOS, RTOS would also offer the same kind of service. That is what the first half statement that goes on. GPOS and RTOS is not different, but they are completely different, or they are different. Why? The service time of RTOS is always constant and known a priori, while the service time of the GPOS would always keep on changing according to the dynamic load onto that particular factors those involved in offering the service into it. This is the prima facie difference between the GPOS, general purpose operating system, and real-time operating system. And that is what, as I always say, that it goes like as the famous author Shiv Khera always says, or he has written a statement in his book, successful people don't do different things. They does it differently. Likewise, I can say RTOS does not offer different services. It offers services differently. And what is that difference is all about? The offering services differently, the mechanism by which services are offered differently is in order to give constant a priori known service time, which makes the system highly deterministic and predicted. And that is what the category of operating system which offers the service time in such way is referred to be as the operating system for making an embedded system as a real-time system, and that operating system is referred to be as a real-time operating system. Am I making the things clear? Hello, is there anyone?
Yes, sir.
Okay, thank you, Devdatta. So we, in a way, I just wanted to narrate the concept that we are looking up to upon, like real-time operating system as such. I think now you might be very clear with the concept that we are calling it as a real-time operating system. Okay, fine. So if I move ahead for this, it is not different than what we already talked of many sessions. RTOS, real-time operating system, also happens to be an interface between hardware and application software, because GPOS or RTOS is the same one, but they are not same. Okay, I'll keep on telling this statement throughout, because now you understand why do I make this two statements which are contradictory to each other in a single statement, right? Okay. The kind of services that, for example, then real-time operating system kernel that is being given. Okay, so I forgot to tell you one thing, that this RTOS or real-time operating system is also called as an HAL, called as a hardware abstraction layer, because of the ability to extract the hardware for the application software at this particular layer. It's also called as an RTOS, RTK, that's real-time kernel, or it's called as an HAL, called as hardware abstraction layer, one and the same thing. Okay, different terminology used in different literature of it. So if you remember the services of this real-time operating system, then these services can be divided loosely according to the requirement of an application. These are not the only services, but majority of the real-time operating system would fetch or would catch up the service of operating system, or majority of the embedded applications would catch up the service of operating system in this particular way. At a central of it, you can see it's in task management. And this particular task management happens to be very central core of the operating system that we call as a scheduler. Basically, scheduler is basically responsible for managing the task as we know it, right? Then we have got the different services. Those can be categorized in the form of inter-task communication and synchronization, timer, device IO supervisor, that's called device driver, for example, and dynamic memory allocation. So these are sample services. Along with this service, along with this particular service, we have different set of services. But let me tell you, the study of real-time operating system, is about the study of mechanism that is being undertaken by operating system in order to provide the service times of these particular services, which are constant and known a priori. Like I should be knowing very appropriately, like by what virtue the task management service of operating system would give me the constant service time, irrespective of the number of tasks which are supposed to be switched. Irrespective of the number of tasks, those are supposed to be switched. What is so special into this real-time operating system? How does the management, or how does this particular mechanism is implemented, by virtue of which this particular task management routine or this particular task management service time, task switching service time, task scheduling service time is always constant, deterministic, and known a priori. Okay. According to me, study of real-time operating system is not only about making use of an API towards an application, but rather study involves understanding the underlying mechanism by which the RTOS or real-time operating system service time happens to be a constant and known a priori. ability of this understanding this mechanism would allow you to write your own operating system. And that is what, if you remember the last discussion, as it was being referred into the misconception of real-time system, that you might not need to write an RTOS because there are several around it. That was a misconception, as I told you, right? And this misconception has eventually proven by Jean Labrosse and his team in the form of MuCOS-2. When they started writing MuCOS-2, was it the case that the real-time operating systems were not in existence? There were plenty, there were many. But none of the operating system, even with an after thorough evaluation, could get best fit to the application that they were doing for. And that's what the reason they thought, like, why not to write their own operating system for their own application, which will fit the requirement of every aspect of the embedded systems, even though it's a tightly constraint, even though it's a memory constraint, even though it's a reactive real time, even though it is only required for the single function for the specific set of services, those are required from operating system. So all the best fitment was possible only because they wrote their own operating system towards their own application. And this is what always we thought to be as an embedded developer's perspective. It's not only what we are getting should be satisfied with the application. On top of that, one should be able to design and devise few new services onto it. And that is what the whole mechanism that this particular real-time operating system would teach us or would refer us in order to write his or her own set of services for his or her own applications. That is one of the significant outcome that one would need to really understand when the real-time operating system study would be completed. Getting it? So according to me, it's not only on making use of API for making the task switching and multitasking and all that, but along with that, understanding the underlying mechanism is extremely important to be able to write one's new services for an application. Okay, so this is the significance of understanding this, or significance of study of this particular real-time operating system kernel. Fine. So with this particular set of services, let's see there are a couple of services which are expected to be built on top of that. Those may be, you might need, like, apart from this, you might need few services, like in addition to these kernel services, many RTOS offers a number of optional add-ons operating system components, such as file system organization, network communication, network management, database management, user interface and graphics that we call GUI. Now, when we say that each of these particular add-on components is included for embedded system as on when required, do you expect that the operating systems like Windows or operating system like Linux, which has got the flooded services in each of this category, there would be some space in memory to accommodate all the services? No, that could not be possible. Even in embedded system, the file system that you are supposed to make use of is completely different than what we make use of into this particular desktop operating systems, isn't it? We are making use of NTFS, or we are making use of a FAT file system, and operating GPOS makes use of this FAT or NTFS. But here in embedded system, most of the time, as you need to build up some relational databases across this particular memory sectors, you might need to go for a this particular flash file system called as a journaling flash file system, JFSS. You might need to make use of this NAND flash. You might to make use of NOR flash, which is completely different set of proposition for exploration of those memory devices. I mean, these kind of file system organization or file system services, those might need to be written by its own, by requirement of an application, isn't it? So there happens the need to write this on all add-on services also, or even the network communication. The device that you are using, for example, making use of the Zigbee, and only Zigbee is what is the requirement of your application, then why one would need to incorporate all the set of services for this wireless communication, for this Bluetooth and USB, and I mean, what not could be the set of this particular network communication modules? Only requirement can be targeted, right? Because memory crunch is there. I mean, these are a few examples where I just wanted to make you aware that network communication, network management, database management, maybe file system organization might be required for your application, but that particular services would be need to cater as on when required by an application the way in which that application needs it. Getting my point? And this is what we say to be as an addition of some add-on services for this embedded application. And that is what it is being written here. Each of these add-on components is included in an embedded system only if its services are needed for implementing the embedded application in order to keep program memory consumption to minimum. As simple as this. This is what we have discussed from last couple of minutes. Okay, fine. So if I go back to this particular diagram, okay, after this particular services, the approaches those are being used in this RTOS is monolithic, microkernel, and decouple. These are the three approaches which are being used into this real-time operating system. Okay. Now, if I just tell you the difference in very quickly, the monolithic operating system where every service of an operating system is bundled together, and monolithic is the word that you might be very familiar with in VLSI called as a monolithic fabrication, monolithic IC fabrication, right? Everything is to be integrated in a seamless manner. So every service is being integrated in a seamless manner. That's we call it a monolithic. It is very hard to detach or it's very hard to configure or deconfigure some set of services because the dependency is so heavy that you have to analyze it thoroughly in order to just get some of the component to be deactivated when you are actually getting into the system. And that is what most of the desktop operating systems, as they are being basically optimized for the throughput requirements, they are being there within monolithic applications, right? When you try and delete some of the OS components, it shouts at you because that component might be a DLL. That means there are dynamic link libraries are being there for this OS. Removing that component might have dependency in the other service that might not work very correctly. That is what there is no recommendation for deletion of any of the OS component in monolithic case of it. In microkernel, as I said you, that it's a very simple, simplistic or minimalistic kernel approach is being there. Only scheduler, for example. Okay. And whatever you required, you just keep on top of that particular scheduler. So just because of the minimalistic service requirements from the scheduler, your kernel becomes micro. Okay. And that's what we call the microkernel approach. The MuCOS2 or free RTOS or QNX or RTX. All these famous RTOSs which are being used in actual applications, in actual products, are basically dealt with this microkernel. I would say that the 90% of the real-time operating systems which are being meant for an embedded systems, stand-alone embedded systems, or small to medium complexity of embedded systems, these makes use of the approach called as a microkernel, where you have started with a minimalistic one and then you keep on adding the services as on been required by the application and the underlying hardware. Okay. While in the monolithic, an example, if I want to quote, I can quote an example called as VxWorks, which is basically full-fledged flooded operating system like your Windows, which is basically used for a very high mission critical hard real-time systems like avionics, aviation electronics, that's we call as an avionics, right? So for the avionic applications, you might need for this particular or any kind of mission critical systems, you might need some computer, for example, in automotive also. Whenever you want to when you are supposed to design some ABS kind of systems, anti-lock braking systems, or any kind of braking component systems, for example, then you have some kind of proprietary automotive operating systems which are being there, which is being defined by SAE or which is defined by any other standard of it. Okay. So these operating systems are basically seamlessly integrated with n number of services. And that is what those are referred to be as an monolithic operating systems. Getting it? And last part of the operating system called decoupled, where is very interesting one. I'll let you know the first of all example called as a real-time Linux. Okay. And this particular real-time Linux is basically a decoupled real-time operating system. What it happens as a real-time Linux as a patch gets executed as the lowest priority thread of, real-time Linux gets executed as the highest priority thread of the entire operating system called as a Linux. So Linux gets executed as the lowest priority thread of RT Linux. So there is a completely coupling, or there is a completely decoupling between the fragments of an application, that which part expect the real-time response and which part does not expect real-time response. The part which does not expect real-time response, not expected to be executed from real-time operating system. They can be executed with normal operating system called Linux. But the part which, for an application which requires an immediate response or some bonded response or deterministic response, predicted response, all these particular tasks are expected to be executed with the services of real-time Linux, which happens to be as the highest priority thread. Because any task, when you're scheduling the task, that task could be ported or migrated to that particular RT Linux. Else otherwise, you can have the task to be flown onto normal Linux. Also, this particular approach is referred to be as it's by design itself, it decouples the real-time and non-real-time task. The operating system is also to be devised, or operating system is to be prepared in order to tackle the task in isolated fashion for real-time and non-real-time tasks. And that is what we meant to be as a decoupled approach in real-time operating system. Getting my point? So these are the approaches that we might need to see for it. Okay. Yes, in the interest of time, I have to stop the discussion at the moment. You might have